Today I'm going to be describing the various methods of integration. And the first method we are going to start with is U substitution. This is a method you should try on all problems before you decide to integrate in a different way. The problem we are going to look at today is the integral of 2x times x squared plus 5 to the negative fourth dx. In order to locate your u, you have to ask yourself, what on the inside of this problem has a derivative that is equal to the outside of the problem? So for instance, in this equation, u is equal to x squared plus 5. This makes the outside of the equation u to the negative fourth once we plug back in. Your du, or your derivative, is now 2x dx. You can now plug back in your equation. You substitute 2x dx for du, and x squared plus 5 now becomes u to the negative fourth. In order to integrate, you must add 1 to your exponent and then divide by that number. In this instance, we get negative 1/3 u to the negative 3. We can then go ahead and plug back in, giving us negative 1/3 times x squared plus 5 to the negative 3 plus c. That is the end of that problem. The next method we will look at is inverse trig. The problem we will be looking at is the integral of e raised to the arcsine x all over the square root of 1 minus x squared dx. Our u in this instance is going to be arcsine x. That is because when you take the derivative of arcsine x, you get 1 over the square root of 1 minus x squared, which then cancels out what you need from the problem. Your integral now becomes e to the u du. When you take the integral of e to the u du, you get e to the u. You can now go ahead and plug back in arcsine, giving you e raised to the arcsine x plus c. The next method we will look at will be integration by parts. For integration by parts, there is 3 ways to identify this problem. The first method is you have to use the equation. The integral of u dv is equal to uv minus the integral of v du. In order to identify what is your u and what is your dv in the equation, you will use the simple acronym LisaCater, which stands for natural log, inverse, algebra, trig, and exponents. You identify integration by parts by noticing that most problems are a function times another function. In this instance, we will look at the integral of x cosine x dx. We choose our u based on LisaCater as previously stated. Therefore, algebra comes before trig, making it that u is equal to x. We now take the derivative and get du is equal to dx. We can now choose our dv based on the fact that we already have our u. In this instance, our dv is equal to cosine x dx. We take the antiderivative of this and get v is equal to sine x. Now going back to our equation of uv minus the integral of v du, we plug in, giving us x sine x minus the integral of sine x dx. As we integrate, we end up with x sine x plus cosine x plus c. And that is how you do integration by parts. Our next method is trig integration. And for this example, we will be using the Pythagorean theorems, specifically sine squared x plus cosine squared x is equal to 1. And we can manipulate this equation in order to solve for what we need. The equation we're going to look at today is the integral of sine raised to the third x cosine squared of x dx. Now, the first step is to go ahead and rewrite this problem, saving a function. And in this case, we're going to save a sine because it is raised to the third. Our new function is now the integral of sine squared x times cosine squared x times sine x dx. And you can go ahead and circle sine x dx if you need to, because this determines your du. So our du is sine x dx. We now take the antiderivative and we end up with u equaling cosine x. This will be useful later when we go ahead and plug in for u. We now rewrite our equation using the Pythagorean theorems as previously stated. We now have the integral of 1 minus cosine squared x times cosine squared x times sine x dx. We can then go ahead and plug in our u that we previously solved for, giving us the integral of 1 minus u squared times u squared du. We go ahead and distribute the u squared, or FOIL as most commonly known, to give us the integral of u squared minus u to the fourth du. You can now integrate properly. This gives you u to the third over 3 plus u to the fifth over 5. You now go ahead and plug back in your u because you need to go back to x's because that was the variable that you started with. You now have cosine x raised to the third over 3 plus cosine x to the fifth over 5 plus c. Our next integration method that we will be looking at is trig substitution. So, when you begin trig substitution, you will be given a couple of identities. The first identity is a squared plus x squared is equal to a tan of theta. A squared minus x squared is equal to a sine of theta. X squared minus a squared is equal to a secant theta. So the problem we will look at today is the integral of the square root of x squared minus 9 all over x. We first need to properly identify which property we have. And as you can see, it is x squared minus a squared, meaning we will use a secant of theta. So we go ahead and understand that our a is equal to 3 because 3 squared gives us 9. We now have our equation. X is equal to 3 secant of theta. We go ahead and find the derivative, giving us dx is equal to 3 secant theta tan theta d theta. Our next step is to simplify the radical. In this problem, our radical was the square root of x squared minus 9. We already discovered that our x is equal to 3 secant of theta, so we go ahead and replace it. We can now distribute the square, leaving us with 9 secant squared theta minus 9. As you can see, you have 9s that can be factored. This radical now turns into the square root of 9 times secant squared theta minus 1. As we distribute this 9, we stop and realize that secant squared of theta minus 1 is a Pythagorean identity and can be changed into the square root of 9 tan squared of theta. As we simplify the radical, we end up with 3 tan of theta. We now have what we need to go ahead and plug in. We change the radical of x squared minus 9 to 3 tan of theta. We take dx and we plug in 3 secant theta tan theta d theta. We plug in for x 3 secant theta. This leaves us with the integral of 3 tan theta, 3 secant theta, tan theta, d theta, all over 3 secant theta. As you may notice, the 3 secant thetas cancel out. This leaves us with the integral of 3 tan squared theta d theta. We can go ahead and plug in our identity property for that, which takes us back to 3, the integral of secant squared theta minus 1 d theta. As we integrate this, we end up with 3 tan theta minus theta. We now go back to our previous equation of x equaling 3 secant theta in order to draw our triangle. We will manipulate this equation so that x over 3 is equal to secant theta. The triangle that is needed for secant is hypotenuse over adjacent. So we will draw a right triangle with the angle in the lower right corner. Our hypotenuse is x, our adjacent is 3, and our opposite is the square root of x squared minus 9. We can now take this equation a step farther and notice that arcsecant of x over 3 is equal to theta. We now go and plug in our equation. So we ended with 3 tan theta minus theta. We will plug in because we need to get back to the variable of x's. This gives us 3 times the square root of x squared minus 9 over 3 minus the arcsecant of x over 3 plus c. And that is the end of that problem. The next method we will look at is partial fractions. For this equation, we are going to look at the integral of negative x plus 1 over x squared plus 3x plus 2. The first step in partial fractions is to realize that you can factor the denominator. This gives us negative x plus 1 all over x plus 1 times x plus 2. The next step is to write your partial fraction. As we notice, both equations are linear. This gives us a over x plus 1 plus b over x plus 2 equaling negative x plus 1 over x plus 1 times x plus 2. Our next step is to get rid of the denominator. We can do this by multiplying each portion by the denominator. This leaves us with x plus 2 times a plus x plus 1 times b equals negative x plus 1. Our next step is to then figure out what makes each equation 0. For a, we can observe that when x is equal to negative 2, a becomes 0. So we plug in and we get a times negative 2 plus 2 plus b times negative 2 plus 1 equals 2 plus 1. This leaves us with b times negative 1 equaling 3. As we divide both sides by negative 1, we can end up with b equaling negative 3. We now go back to our other equation and realize that x equaling negative 1 will make b equal 0. So we go ahead and plug in. A times negative 1 plus 2 plus b times negative 1 plus 1 equals 1 plus 1. A times 1 plus b times 0 is equal to 2. 2 divided by 1 gives us a equaling 2. We now take our a and our b and we plug back into our function. This gives us 2 integral of 1 over x plus 1 dx plus negative 3 integral 1 over x plus 2 dx. As we integrate both sides separately, we end up with 2 natural log of x plus 1 plus negative 3 natural log of x plus 2 plus c. Your problem is now solved. These are the various methods of integration and are useful